Grade 12 University Physics, Unit 4, Wave Nature of Light, Lesson 3, Interference of Waves in Thin Films. Here's our question. A coating 177.4 nanometers thick is applied to a lens to minimize reflections. The respective indices of refraction of the coating and of the lens material are 1.55 and 1.48. What wavelength in air is minimally reflected for normal incidence in the smallest thickness? Alright, so let's look at what this actually looks like. So here we have a coating on top of glass. And of course, we have air on top of the coating. So we'll draw those and we'll write their respective indices of refraction. Now, let's take a ray of light coming from air and hitting the coating. It is both going to reflect and refract. Now let's trace and follow these two rays, the one that's reflected and the one that's refracted. The one that's reflected simply bounces back. But because it's bouncing off of a material with a higher index of refraction, it gets inverted. The one transmitted through into the coating does not get inverted. Similarly, when the second ray reflects off of the glass and comes back, it's reflecting off of a material with a lower index of refraction, and again, does not get inverted. So here we have ray 1 inverted and ray 2 not inverted, but ray 2 has an additional path to travel. Now let's say the thickness of the coating is exactly 1/4 wavelength. So it's going to have to travel 1/4 wavelength down and respectively 1/4 wavelength back up. So this puts it back into phase with ray 1. So if this were the case, ray 1 and ray 2 would interfere constructively and you would see that light. But the question is asking for what wavelength in air is minimally reflected, so it wants destructive interference. So let's look at what if the thickness was actually 1/2 wavelength. If this were the case, it would travel 1/2 wavelength down and 1/2 wavelength back up for a total of 1 wavelength. This puts it back out of phase with the first ray, and they will interfere destructively. So now that we know that the thickness would have to be a 1/2 wavelength for the coating, we need to figure out what the wavelength actually is. But the question says, what's the wavelength in air? And the wavelength of this light in air will not be the same as it is in the coating. When it transmits into the coating, the wavelength will actually decrease. So we need to use our previous equations to actually figure out what the wavelength would be in the coating. So to do that, we take the ratio of the wavelengths and the inverse of those ratios for the indices of refraction. We can solve for the wavelength of the coating equal to the wavelength of air divided by the index of refraction of the coating. The index of refraction of air is just 1, so I just left that out. Now, taking this and subbing it into the equation we have for the thickness equal to 1/2 wavelength for the coating, we can rearrange and get that our wavelength in air is 2 times the thickness times the index of refraction for the coating. Subbing in our numbers, we get the wavelength in air to be 550 nanometers.